Goedemorgen. Thanks for having me here. It's a pleasure. It's my first time in Netherlands, and I'm happy that it is for this wonderful conference. I will start with the question. Do you know what is the smallest bone in the body, and if you know where it is? Ear? Fantastic, yes. It's right in the ear. It's called the stapes. The stapes is a very, very tiny bone. It has 2 to 3 millimeters in length. It's that little red thingy that you see here. And it's responsible to transmit acoustic vibrations from the outside world to the hearing organ, the cochlea here in blue. It's so tiny that it's smaller than a grain of rice. And well, it's located close to the cochlea. And the cochlea is also very, very tiny. The cochlea itself has about 10 millimeters, and it is pretty much like the size of a pea, the vegetable. When clinicians and surgeons do the surgery, it's a very tricky and delicate operation. You can see maybe this whole complex system, and it gets even more complex when you want to treat human hearing issues. So one of the therapeutic procedures to treat deafness is through cochlear implant surgery. And that's done by inserting a little electrode inside of the cochlea, the little snail over here. But you can imagine that the cochlea is really, really tiny. So this is a one-to-one printout of the cochlea. I have it here also in my hands if you want to then see later. It's super, super small. And now you can imagine the difficulty to insert an implant, to first find a trajectory, to drill the hole through the skull, behind the ear, not to hit the critical nerves, otherwise the patient could stay paralyzed on one side of the face, or could potentially lose the sensation of taste. Clearly nothing that you would want. So our surgeons need to plan a lot. So they plan a lot by opening images. So they acquire CT images and MRI images and so on, but mostly CT. So here you see, for example, an image of a CT image from the skull of a patient. And also here you see highlighted like where is the cochlea itself on the image. So before the surgery, you would want to plan like well, not to hit the critical organs and so on, and also to find a way to this tiny organ, to find a tiny opening inside. So the knowledge of geometry is even more important. And so let's dig in. Hi, nice to meet you. I'm Jan, and I'm really passionate about medical imaging, mostly for human hearing and human hearts. So you will see a lot of maybe interspersed information about the hearts and the ears, and I hope it's going to also inspire you to see your own domains. And we will go and have a look at some visualization tools using libraries like PyVista, trimesh, and Open3D, and to at least somehow give some toolbox that we can all use to better visualize in 3D. I usually work with machine learning, but this talk is not about machine learning today. If you have any questions about machine learning, I would be really happy to talk about machine learning with you somewhere in the hallway or in the room that we have assigned. We will talk about visualizing meshes and 3D structures. We will also talk about how to process those meshes, and we'll touch upon how to build apps using these libraries and how to do research, or how can these libraries help us in academic research or publishing. So to start, let's start to visualize the meshes and geometries. We will use PyVista, and Mesh.io is like kind of the backend for PyVista to load data. So it's actually very simple in Python these days. If with libraries like PyVista, the only thing you need to do is to import the library and do PyVista read and the name of the file where the mesh is located. And the mesh, many formats are supported. There's definitely no need to be worried that your will not be there. But reading a mesh, like what is a mesh? Well, a mesh itself is not that much more than like a very simplified representation of some usually 3D object. Sometimes surface, sometimes volume, but in this talk we'll mostly concern ourselves about the surface. And so to construct a mesh, you need some set of points. So some set of points in 3D space, and you need to know how those points are connected. And the traditional way in computer graphics and in our field is also to connect the points, mostly with triangles, because triangles are computationally efficient, but sometimes you can actually use squares instead of triangles. So that's what you need to define. You need to define like what are the vertices, the points, and what are the faces. Those are those little primitives that connect the points together. And in between, the lines in between the points are called the edges. So in PyVista, this visualization library, most of this data is stored as a polydata object. And the beauty of this representation is that you can then use this object in a very unified interface. No matter whether you work with meshes or images and so on, it's actually very easy and very user-friendly. So if we now connect the triangles together, we keep connecting triangles. Keep connecting dots and triangles, and well, from very simple objects, you can start to construct something more complex, like, for example, the rabbit here, or we have the cochlea or the human heart. Now, instead of calling the plot function on the mesh itself, we can do something more complex with PyVista. We can start to compose our scene, and that we can do by first defining the plotter, so-called plotter. That's this object that manages the scene, the rendering of the scene. And then we can add mesh or add volume, and these kind of objects we can always add to the mesh. And then once we do PL show, it all renders to the scene. Well, but that's probably not what you want to do from medical images. You don't want to define your meshes yourself. You usually want to define them from the image content. And one way is to use those tools to manually segment, like you draw essentially like a paintbrush across the image in 3D, so it takes a lot of time. So we have ways to do it with machine learning. For example, there are lots of different ways to do it. One very common way these days is to just download a unit architecture of a convolutional neural network, and you feed it pairs of information, like what is the source, what is the target, and then you train the network in between the black box to reproduce what you gave it. And then if there's any difference, you backpropagate. But as I said, this is not the point of this talk. Today we are visualizing. So we have this segment magic function here, which is anything you want that segments the image, and that returns you another image which contains essentially a binary or probability map of which pixel, or in medical imaging it's called voxel because it's in 3D, which voxel is likely to be the structure of interest. So in this case, we have an example of an image of a left atrium. So it's a part of the heart. This is the chamber that pumps the deoxygenated blood to the so-called left ventricle, which then pumps it through the aorta to the body. So that's thanks to that we can actually be alive. So one way to then so we get two images. One is this segmentation, which is this map per voxel. We get a value, but how can we visualize that as a mesh, as a 3D object? And one way is to use this contour function, which is computing the isocontour with a fast marching algorithm or something similar, and that gives us a mesh. And again, we can use a plotter, and we can then combine our meshes. It was really nice about PyVista that they have thought a lot about how to interact with these objects. And so instead of only showing the mesh of the image, which would be just actually a black box, because the image is a volume. So first, you can either render that, or you can slice into the volume. And so there's this slice orthogonal function, for example, or you can slice like any oblique direction to see inside what's happening. And then you show. But, well, that's maybe some of you are not using medical imaging, and you want to construct your own meshes for your own applications. And there are lots of primitives you can construct the meshes from, like cylinders, arrows, spheres, cubes, polygons, and so on. And it all follows the very same interface, like how you show, how you combine things, how you add properties, and so on. So, but maybe you are not, you don't want to model that yourself, and you have your CAD software, which exports you STL meshes, for example, which you want to show somehow. Maybe you're an architect, and you want to see the building in some 3D view together with something else. So, same. I think I would like to point out that this PyVista library has a fantastic gallery of examples. So if you would want to do any 3D visualization, go and check the gallery, and it's quite likely that you will find something similar to your application that you can easily adapt. And what if you don't use even meshes and you want to show some points? Maybe you are working with LiDAR cameras of the cars and you want to just render points in 3D. Yes, you can do that in Matplotlib. It's totally doable to do it, that you can move things around, but it's not that easy to combine with other things like meshes and other information that you would want. Whereas here, the same thing, you just either append the things to the plotter, or you just plot the polydata object that you create. The interesting thing that is in PyVista is that you can give colors to the object through properties of the mesh. And you can give the properties either to the vertices or to the faces. And then you can decide which one matter to you. If you want to something in between, you can interpolate. But that's all handled by PyVista for you. Well, then things to visualize curves. In my application, we are working with cochlear implants. And the cochlear implant itself is a tube that deforms within the sphere, within the spiral of the cochlea. And you want to model that. You want to be able to see where it goes and how it looks, whether it touches some critical structures or not. Maybe you are modeling electrical wiring, maybe something else, and you would want to see some tubes. There are plenty of applications for tubes, even if you just want to thicken a curve. That's also a pretty good application. But if we go from the curves, now we start to have these objects which are more complex and which start to have properties. If you start to simulate things, you want to assign how it should look like at every point. So in my previous application, some years ago, we were doing a simulation of electrical propagation through the heart. And you would want to see the wave of polarization that goes through the cells in a simulated model of the heart. And that's exactly why you can assign these properties, like colors, to the meshes themselves. In some application, again, maybe an architect or mechanical engineer want to model strains, forces, and so on within some simulated materials. So once you compute those forces, PyVista does not compute the forces for you. You have to do it somewhere else in some simulation software. Then you can visualize how those things look like. And of course, like once you show colors, you can also do some other information like glyphs. So if you want some currents, you want some curls or some streamlines, you can all do that. And it's again following the same interface at mesh, and then maybe defining some scalars. The scalars is telling you which property from the array should be taken to visualize, and that's very much it. So once we show everything that we can, we might want to start to introspecting into our objects. And if the object is totally solid, you cannot see anything inside. So one way to see something inside, as a surgeon would do, is to cut through. So you cut and open. And you define the cut by defining the plane of the cutting plane. And that is through the origin and the normal of the plane. An extremely simple operation, and also very practical in many ways. Also, there are ways to do it like automatically through the 3 orthogonal axes, x, y, z, so that you don't need to do anything yourself. Sometimes it's totally fine to do. And for the ones that are more inclined to do graphics and don't want to see only meshes, but want to see some more pretty visualization, there is a support for physically based rendering where you can specify the material properties, like if it's metallic, roughness, and diffusibility. And you render the mesh. What I show here, in addition to the rendering of over here, this is PBR, but you need to turn physically based rendering to true, and then it happens, it looks like this. The CPOS is the camera position. So we have not talked much about the camera yet, but it's fairly straightforward. You tell the scene, like where is the camera located and where it is looking. So it's a direction plus the position. Then you can also define what is the frustrum, or the so-called like the field of view of the camera, like where you start cutting, where you stop cutting, and what matters to you for the rendering. Then other things like, okay, you start to visualize, you start to add glyphs, and it starts to look good. But what if you want to change some things, some parameters of your computation? You want to see how it behaves between 2 operations. And you want to have some sliders, checkboxes, and these kind of things. It's all implemented there. Through some callbacks, you can see how your 3D scene changes if you change something. For example, there's this mesh threshold implemented, but you can also do something custom as a callback to some slider change. So I think this library is very useful for visualization. But in my field, when we work with a lot of medical images, we have sometimes issues with quality of the data that comes in. And there's usually the saying that data science is like garbage in, garbage out. And you want to filter out and you want to correct the information that comes to your machine learning models so that you don't learn something that's totally wrong. And so here I took an example from this, using this left atrial segmentation challenge dataset that's available for anyone to download. And it's a dataset that's using MRI images to train models of the left atrium. Again, this chamber that pumps the oxygenated blood from the lungs to the heart. And there's a little snippet here. And just if I would go briefly through that. So if we have some, for example, a folder which contains a lot of images, for example, in this nifty NII format, we can find all of them by globbing. We find the list of images, and we can give the list directly to PyVista. We can then iterate over all the images and the labels. The labels are the segmentations. And we extract the contour from the label. We get images which are not acquired in the same center, in the same machine. The patient is not always in the same position. So if you want to compare anything, you want to kind of bring things to the same reference frame. So that's why we compute the center of mass, and we subtract, we move the surface by the center of mass to have it all centered. I'll do the same thing for the images. And I think now we can define subplots. So we can define a grid of things that are connected, and we can define slices and so on. We finally, when we are happy with that, we can link views. That means that if we move one grid, everything else will change. But I think I was talking too much. There's also this callback toggle visibility, which can change some parameters of the actors or the objects on the scene. But let's just see how it looks like then. Like with very few lines of code, we can see the whole data set. We can cut through the data set. We can see the left atrium. All the red objects are left atria of different patients. So that now you can appreciate the differences, like how many pulmonary veins are coming in. Like some people have more, some people have less, but mostly it's 4. And you can also see like how well it looks on the image. So what we usually look at in our field is that we want to see like good correspondence with the image content and the contours of the 3D segmented objects. And I think that this dataset is well done. So there are no issues, but if there were, we would be able to detect that. But now we have a large data set of images, and we want to see like how the patients look like across the space from our population. So we can find some mapping functions like dimensionality reduction things. Like here we use some UMAP function that projected this higher dimensional representation of each shape to 2 dimensions. So X, Y, so dimension 0 and dimension 1. And now we can use PyVista to draw corresponding shape at each XY coordinate. So at some point, you might see that there are clusters of diseases. The different colors mean that there are some differences between the patients. And you can totally see now that if you would draw a line like straight diagonally here, you would be able to tell with fairly good accuracy that these patients are, or actually these people are healthy, and there is potentially something wrong in this group. But you can also play. You can add widgets. So not only you can do these projections, but these projections have some other parameters. You want to find like which parameters are the best ones. So you can add widgets that have sliders and then see how your algorithms behave under those changes. So we saw how to visualize the meshes, and let's have a brief look at how to process them. And for that, we can use PyVista again. It has quite a good library of processing functions. And there are different 3D geometry libraries like trimesh and Object 3D, which can be adapted, or you can write some little adapter that can talk to PyVista and vice versa. Let's have a look at that. So in trimesh, there is a very interesting function, for example, that's called iterative closest point, or they also call it mesh other in the module registration. And what that function can let you do is to take 2 different shapes and find the best alignment of the shapes, so that the distance the Euclidean distance between the shapes is minimized. And of course, that matters to us because we don't want to only move everything to the center as we did in the previous example, but we also want to rotate it such that we can then start to compare the arteries, so that the arteries are roughly at the same position. And so, yeah, you do need to write a little adapter. It's essentially taking the mesh and extracting the faces from the mesh and reshaping it a little bit. And then we can construct the new mesh in the trimesh format, and it all works just fine. I believe that PyVista has a potential to become this lingua franca, essentially, like what we have in data science or in general, like NumPy. The libraries now talk, NumPy arrays between each other. And it's a pretty nice, happy ecosystem because of that. So we can align. We can also smooth. So images coming from, meshes coming from images. I'm not sure if it's really visible here, but you could probably see the images are rastered. So depending on the resolution of the scanner, you get bigger or smaller steps. And of course, you don't want steps because it's not natural. Like our hearts or our cochlea don't have steps. We want something smooth. And one way to do it is to call the smooth function, which applies some Laplacian smoothing over the surface so that you get something that removes the points. You can connect it with Open3D to get some other functions like octree to find nearest neighbors really quickly, and so on. There is, again, you go through you construct it through the mesh dot points, which is essentially an NumPy array containing the points of the mesh. And, well, finally, the last part is how to build apps and do research. So this is an example of a nice library that uses PyVista with Qt. It's open source on GitHub. That's called VesselVio. That is a great example of how to build a Qt application with Python using these 3D visualization libraries. And I think it contains all that you would need to start, but it's even simpler. The second thing that I would like to say that now it's become much easier to take a segmentation, read the image, take the segmentation, then get the contour of the segmentation, do some little post-processing like finding the largest component, smooth it out, cleaning it, and simplify the mesh, and so then you can then print some organ that you can use for teaching, or you can use, eventually, hopefully in the future, we can use some spare parts for our own bodies. And lastly, it's a very nice tool to visualize your research, to illustrate the publications that you make. Because it's very simple, it doesn't take much time to construct good-looking material that conveys the message. Like here, it's from one publication on the cochlear imaging pipeline. And if you're interested there, I can give you the link to that work. So my key takeaways is that 3D is beautiful, and we should be using it much more. I think we should start to explore these libraries also for not only meshes, and to maybe explore what is possible. And yeah, let's visualize this thing. Let's process the things we want to visualize, and let's build some nice applications. And give it a try today. And I wonder, like, so now you all remember, like, where is the smallest bone in the ear, right? Thank you.
All right. Any questions? You?
Yeah, fantastic talk. Very interesting.
Thank you.
I played a bit with 3D rendering, and I know that especially if you have interactive visuals, then 3D rendering, especially physically based rendering, can become very slow and very heavy, right? So can you elaborate a bit on how efficient the engine is that is used by PyVista?
I will just repeat the question for the stream. So the question was about how efficient the engine is that is rendering these meshes.
I think it's all right, but if you want something more efficient, then the Open3D library is a much better optimized library from what I feel. When I use physical-based rendering on my laptop, it starts to burn, like it's almost unusable. But it produces good-looking images. It's nice, but just it's heavy. That's true.
So that's more for images than videos, then for interactive.
Yeah, probably I would not use it for videos. Yes, that's a great question. Thank you.
Another question?
There's some open source 3D modeling software already like available, and some is even Python-based. I think Blender has some Python-based thing. Is PyVista, does it have an overlap, for instance, with like, for instance, programs like Blender or like other used programs?
I think that you can import Blender-generated graphics into PyVista. You could do it vice versa. You could export those objects into any format that Blender supports. I think that PyVista is more oriented, after all, to work with kind of like NumPy arrays or this kind of like tensor information. But still, you could export or import in both ways. But
is the syntax then like similar, for instance, if you would be programming in Blender or programming in OpenSCAD, or something completely new to learn in PyVista?
I have not used that, so I can't answer the question, but I will look into that. Thank you.
Another question? I can also give you.
Yeah, thank you. At the Fab Lab, we do a lot of 3D scanning, and then you end up with an outside map of a person, but that's a hollow mesh. And then we want to 3D print it, and then we have to put cylinders and stuff. Like there's a small functionality to fill it, but I was wondering, like, does PyVista have building functionality to fill the inside of a model for 3D printing?
There is, you can triangulate, and if you want to fill in if you would want not like a surface mesh, but a volumetric mesh, there's like this PyMesh library which can do that. I think it's using 8-gen in behind the scenes, which is GPL, so maybe it doesn't work for some. But if you want to just complete the mesh, I wonder, yeah, the Open3D has, for example, how you can compute the hull shape of the empty mesh, or I don't know if the information is missing. Then what how can you fill it in?
Yeah. There's like a lot of holes in there. Like as a person, I can see like, oh, I know how to fill this.
Right.
But if I would fill it like let the software go wild, then I can also imagine that it would just spill out everywhere. And,
Yeah, I think it's a very difficult, even academic still question, like how to fill in the information, how to fill the holes. And there are, I think in Open3D you have hole filling algorithms. I have not used them, but I hope.
Sorry, just are there any more questions? I think we have room for one short question. Yes.
What is the support of PyVista for not watertight meshes? So, is there some tool for that, or is that?
Yeah, you can visualize not watertight meshes. You would just have holes in the mesh, right?
And what about so measuring distances or use it in an interactive way to do assessment about the
so for measuring
topography?
Distances, you mean like between a point and the whole mesh, or between two meshes, for example,
Yeah,
something like that?
Exactly.
I think that trimesh has support for some distance computation, or even Open3D has some KD3 implementation of some quick distance computation between two meshes.
Okay, thank you.
Sure.
All right, let's leave it there. Thank you all. Thank you very much for this interesting talk. We have a present from Pygrunn for you.
Thank you.
It's all right. One more applause for Jan.